Now we'll discuss about equivalence relation, one of the most important things that will come handy many times throughout this journey. So, from the previous segments, you have learned about three properties of a relation. Now we say, a relation is called an equivalence relation if it follows all those properties, that is if it is reflexive, symmetric and transitive. Let's see an example. Say we have a relation on A to B, with A plus B is an even number. Here, A and B is in set Z. Now we have to verify if it is an equivalence relation or not. So, first of all, notice whatever A is, even or odd, if we add two A's together we'll get 2A, which is even. So, the relation is reflexive. Then see, in this additive relation, order of the numbers doesn't matter, that is, A plus B is equal to B plus A for all such A and B. So it's symmetric. Now suppose we have two relation. One on A and B, and the others is on B and C. So, A plus B and B, plus C is even. Now add them together. Then you'll get twice B, plus A, plus C. This expression has to even. As 2B, is already an even number. The only way the whole expression can be even, if and only if A plus C is even, so the relation is also transitive. That ends the proof. There are many other good examples. Like, if we define a relation to A and B with, their difference be in the integer set, it'll be an equivalence relation. And the proofs are so straightforward. All you have to do is, show the relation is transitive, symmetric and reflexive. But there are some complicated cases. I won't show them right now. But we'll encounter them later. Now let's see some important definitions. Let's define an equivalence relation on set S. If A is the elements of S, then we say the equivalence class of A is the set of all B, such that A and B has an equivalence relation. Another definition. Let S be a set, and let T be a set of non-empty subsets of S. We say that T is a partition of S, if every A of S lies in exactly one set in T. An example is shown. Now an important theorem. Let's define an equivalence relation on set S. Then the equivalence classes with respect to that relation, form a partition of S. In particular, if A is on S, then if it belongs to the classes of A, and, if furthermore it belongs to the classes of B, then the classes of A is equal to the classes of B. What it basically tried to imply is, the intersection of all those partition of set S, is an empty set, that is they don't have any common element. Which further implies that, an element of set S, can be on only one of the partition sets. I would recommend you to check out the proof. Let's see another example. In the example 1.5, we had defined an equivalence relation on A and B if A plus B is even. Let's start with B is equal to 0. Then the classes of 0 are all even numbers. And then let's take B is equal to 1, then the equivalence class of 1 is, all odd numbers. Notice, the classes of 0 and 1 span the whole Z set. But what if we took 13 and 16? Well, we would get the same class like 0 and 1. So, there are only two classes of that relation. And we can say that, on this relation, the partition of set Z, are the classes, 0 and 1.